Well,
All right.
looks like it's my turn. Mary Jo and Paul, thank you so much I always love hanging out with them. They're the best. But right now, I get to talk to one of my favorite topics with one of my favorite people. We're going to be talking about Azure with Mark Russinovich, the CTO of Microsoft Azure. Welcome to Build 2020, Build Digital. Are you there, Mark?
I'm here.
How you doing, buddy?
Doing good. How about you?
Good. Well, you stopped inviting me to the barbecues, like even before the incidents that have been happening. What happened? Is it something I said?
I know, I saw it coming.
Well, look, I'm going to start off. We have a good amount of time, and hopefully we can get some questions from the audience. If you can submit them, use the hashtag MSBuild, by the way. You're Azure's CTO. What does that even mean?
It means, well, so the summary of what I do when I talk to people and they say, what is the CTO? I lead technical strategy and architecture for the Azure platform. So every CTO at different companies and different organizations does things slightly differently. I spend about 80% of my time with the engineering teams. And then the other 20% of the time, it's talking to customers, talking to analysts and press, and going out and doing things like this, like speaking at conferences.
So let's start with this thing, because I heard that you have something called the Azure Office of the CTO, and you're doing a lot of cool stuff. Tell us about the team you're building over there.
Yeah, well, when I started in this role, effectively back in 2010 when I joined Azure, I worked as an individual contributor. And as Azure has gotten larger and more companies and services inside the company depend on it, I've needed to scale my reach. Before I could just speak to the engineering team and it was a few hundred people. Now we're talking tens of thousands of people. And so I think to magnify the impact that I can have, I've started to grow a team. And the team actually consists of 4 sub-teams that really, I think, are benefit from being centrally placed in the organization, where we can look at things horizontally and look at the future, where the engineering teams maybe are focused on their particular segment and focused on near term. And so some of the 4 teams that I've got underneath me start with the open source ecosystem team, which manages our open source partnerships as well as guides Microsoft internally on adoption and management of open source. I also and our engagement with foundations, for example. Sarah Novotny is part of that team, and she represents us in the Linux Foundation. I also have a quality engineering team, which I started in the spring of last year, which is focused on what we can do centrally to look at how we can lift all boats across Azure with from a common engineering quality perspective. So processes and also tools, not that we'll develop them inside this team, but we'll help figure out by talking to teams across Azure and across the company of what kind of tools would help raise the quality of our services. I also have a relatively new team, which is the AI infrastructure service team, which is focused on creating a software layer to manage things like the AI supercomputers that Satya mentioned. And then finally, I've also got an incubations team, which is looking at kind of projects that look promising and interesting, but don't really fit into an engineering team, at least not for initial exploration, and then incubating them inside this team, working with the engineering teams that might be targets for a transfer, and proving those out, and then eventually delivering them.
So let's talk about the incubation team, because that feels like this is like Azure.next kind of stuff. Tell us what's going on in that team.
So that team actually, it started kind of accidentally. I've not seen really incubations teams have success, at least ones that have been organized with a goal, a charter of incubating and doing technology transfer and engineering. So I've been somewhat skeptical, and I don't even know, I didn't know how to go about creating a successful engineering team or incubations team. But the fact is I started to hire technical assistants, and those technical assistants like Hashi Bai, who Yaron Schneider, were extremely creative and started to come up with ideas and say, hey, this looks like something that might be interesting. I just worked on this project over the last week on my own time, and what do you think of it? And what came out of that were some very successful transfers into engineering teams, some really promising technologies. And I thought, if I continue to hire creative people like this, and I put engineering structure around it and some structure around how we explore incubations and then kind of stage gate them into subsequent stages of investment and then work with the engineering teams, maybe we have something here that can go after things that are falling through the cracks.
So, can you give me an example of some of the things that have been falling through the cracks that your incubation team has picked up and made some cool stuff out of?
Yeah, well, one of the early incubations that came out and is in production and seems to be quite successful is CADA, the Kubernetes event-driven autoscaler. So that came out of the team, the engineers in the team saying, hey, it looks like there's not a really great way to scale to zero and to scale off arbitrary metrics in Kubernetes without the kind of existing approaches bringing a whole lot of scaffolding. So if we could make something lightweight and very extensible, that would be something that would be very useful to the Kubernetes community. And hence, they prototyped CADA, incubated it. We engaged with the Azure Compute team on it and started to co-engineer it, and then did a transfer of it from the incubations team to the compute team. The compute team took it, and now it's a CNCF project, sandbox project. So great example of going from idea, prototype, building it up, incubating, engaging with an engineering team, and then transferring it out. And now it's out in the world and being adopted.
So help me out with CADA, because you said that we need to scale Kubernetes, but I thought Kubernetes was for scaling. What you know what I'm saying? So what problem is this solving?
So it's not scaling Kubernetes itself, it's scaling applications that run on Kubernetes. So for example, if you've got a web front end, a simple way to scale would be a metric off of CPU usage, CPU utilization, CPU load off of on the pods. When they go above a certain rate, create another one. But what CADA brings to the table is the ability to specify effectively arbitrary metrics. So you could say when this queue of incoming requests reaches a certain depth, then scale out, because we're not processing those items quickly enough.
For those that maybe are new to Kubernetes, my understanding of Kubernetes is you give it a desired state, and then it tries really hard to just have that desired state. The only thing you're saying you can do is tell it if a CPU goes over X, then make a new container. You're saying with CADA, you can do arbitrary things? Like, can you give me an example of the kinds of things you can use to scale in that with CADA?
Yeah, well, so Kubernetes does have scaling capability built into it, and there's also other autoscalers for Kubernetes. What CADA does is bring in the ability to plug in very easily other sources for scaling signals. So the one I mentioned is you could say when a Redis cache, when it's got a certain depth in it, when a service bus queue reaches a certain depth, when the load on this other service reaches a certain level, then scale the front ends or scale this microservice out or scale it down if it drops below a certain threshold.
I see. So now that we're kind of like getting into all of your, because I'm going to call it the Skunkworks team just for purposes of this interview, but then we won't tell anyone else about this. What else is the Skunkworks team working on? Because now I'm really interested, because this probably isn't the only thing that you're doing.
No, it's not. There's a variety of different projects. One of them is Cyrus, another project that is out there in open source. And I think that's one of the principles also that we're trying to follow is let's just do everything open source and engage the community. Cyrus is a scale to zero autoscaler for Kubernetes. So, and what that means is when you've got a front end, for example, listening to requests, it's difficult to scale it down to zero, meaning if nobody needs the resources, delete the last pod. What you require for that is basically something that's listening for incoming requests as a proxy. And when it sees an incoming request, then goes and spins up the target pod. So acting on its behalf, sitting there listening, waiting for requests, and that lets you scale down to zero, meaning you don't have any running instances of your web front end pods. So that's one of the projects that's out there. But some of the big ones, and I think the ones that really gave me confidence that this model can really work, on top of those ones that were there, are two projects that we launched right before Ignite. One is called Open Application Model, which is looking at an application deployment model that can work in a serverless environment as well as on Kubernetes or other infrastructures, and really focuses on developers and how they describe their applications. So the idea is developer describes their app, and then they can take that app and run it on a serverless platform without modifying that description of the application, turn around and running it on a Kubernetes cluster that might be on-prem. So it's really part of that cloud edge consistency story that we're working on at Microsoft, and that you're going to hear Kevin Scott talk about tomorrow morning.
So can I ask, let's pause right here, because Like,
Sure.
look, the mantra for me is anytime you have a problem and you solve it with distributed systems, then you have two problems, right? I mean, that's what I
Right.
learned
Yeah.
when I went to school. How does open application model help with making distributed applications easier to start up? Because like I said, it's a hard thing.
Yeah. Well, so to be clear, it's an application model in the sense that it describes the topology and requirements of your application in a way that an infrastructure that is going to go and deploy it knows how to go about doing that for you. So this is where you would say, I've got 5 microservices. Here's the front end. It needs to be this type of pod. They need GPUs. They need to scale to this. They need to be able to talk to this other microservice, but other microservices shouldn't be able to talk to it. It's going to be using this version of this Docker image. I've got this autoscaler in front of it. I've got this ingress controller over here on top of this autoscaler. So describing the structure, the topology of your application is what Ohm is aimed at. It's not about making it easy to write a distributed application. But since you mentioned that, we do have a second project, which is even more exciting to me, and that's called Dapper, which is this distributed application runtime, which is basically a substrate that makes it really easy to write distributed applications.
So this is where I got confused because we had this chat at Ignite. I think it was, I don't know, feels like 70 years ago.
Yeah.
But I was confused between what Ohm was, Open Application Model, and Dapper. You're saying that Ohm is more of a specification and Dapper is an implementation, or am I off here?
Well, Ohm is more about how you would describe the structure of an application. It has nothing to do with what code is inside that application. So developer doesn't need to do anything to use Ohm. It is a way of simply describing multiple pieces of an application and how they relate to one another. So it's not really something for programmers per se in their day-to-day development. It doesn't solve or help with distributed systems problems other than the deployment of a distributed system or the upgrade of a distributed system. Dapper, on the other hand, is about making it easy for developers to write cloud-native distributed systems, ones that are resilient and scale out and that are portable across the client and edge and across different cloud environments as well. So really, they're both kind of effectively specs as well as implementations. Ohm is a spec. There's an implementation for Kubernetes called Rudder for it. There'll be implementations there. Ali Cloud has an implementation as well for their service that is based off of the Ohm spec. Dapper itself has one implementation that we're working on that is kind of, here's the APIs that it exposes, here's the implementation for it, but different purposes. Ohm is about structure of an application, deploying it, upgrading it. Dapper is about how you write the application, make it easy to write a distributed app.
Got it. So Ohm is like the infrastructure, Dapper is how it runs. And now that we're looking at, I want to take a look at Dapper. How does it make it easier for me to build a distributed application? Is it language specific? Is it language agnostic? I mean, how does it actually work? Because to me, it's surprising that you could make a layer for that somehow.
Yeah. Well, so the key aspect of Dapper is that it's a sidecar architecture. And what that means is that it provides its services through a local endpoint to your compute, whether it's compute sitting on a laptop or compute sitting in a container in a Kubernetes cluster. Your code interacts with Dapper services by calling a local endpoint, either through HTTP or gRPC. And it consists of a bunch of building blocks that it exposes through this sidecar API framework. And those building blocks include things like, hey, if you want to save some data to a state store, call the Dapper State Store API. If you want to pub sub, put a message in a queue that another microservice can consume, call the Dapper pub sub binding building block. If you want to invoke another service directly, rather than having to go use DNS and figure out where it is and set up the connection and authenticate it, you simply call into the service invocation endpoint that say, call this microservice C and pass it this payload. So it takes care, it abstracts through this interface all of the gory details of state store management, pub sub, all the integrations with other services that without it, a developer would be forced to get those SDKs for those different services, learn them, learn how to their particular APIs, put in all the coding to do retries and throttling. All of that is done at the common building block layer of Dapper. So developers can just simply invoke its APIs and take advantage of all that.
Can you give me an example of how a developer would take advantage of this? Because like I'm understanding like intuitively, oh, okay, so you're simplifying a lot of the issues with the distributed systems by having a sidecar layer that it's like your little robot that takes care of things. But I'm having a hard time visualizing in an actual kind of application or example. Do you have something?
I can show you a little demo.
Let's share your screen. Let's do it.
Yeah.
So let's share your screen. It's okay. We can share screens here. Because like I said, and as you get your screen up, like it's really hard for me to, like I said, distributed systems are awesome, but they're also super hard. So let's take a look at what you got. All right, we got your screen, bud.
So here's a little sample app. So this sample app, you can see the architecture for it here on the screen. This is an app. You can see 3 Dapper sidecars there. They're shown in white with the little Dapper logo.
Nice.
And then you can see that what those are doing is reading from Twitter. Now, if you think about it, I want to read tweets from Twitter, and I want to perform an action whenever I see tweets that are interesting. Those actions in this application are to look at the sentiment. So this is a sentiment processor over here that I want to invoke from the Twitter provider, which is reading those tweets. I also want to save those tweets to a Redis database. And when I get back a sentiment score, I want to send the tweet with the sentiment score to a tweet viewer, which is going to be presenting a view of those tweets in a website. And I'm going to do that through Redis. Now, if you take a step back and look at this architecture here, and you think about doing it without Dapper's help, what we've asked the developer to do is to go talk to Twitter, call its API, read the tweets out, load in a Redis SDK, store the tweets in Redis, figure out how to invoke this other service here, the sentiment processor, by calling it with the tweet, getting back a sentiment score, and then publishing it through this scored tweet Redis cache instance to the tweet viewer. And by the way, we've decided that we're going to write the Twitter provider, the sentiment processor in Node.js, and we're going to write the tweet viewer in Go. So we're using multiple languages. Now with Dapper's help, the developers don't need to really interact with the Twitter API at all. They interact with the local Dapper endpoint for the Twitter binding, so they get the tweets just handed to them. They don't need to learn Redis or Redis cache. They simply call the Dapper state store building block and say store it, and then underneath the hood, the Redis component for that does the magic of storing it in Redis. Same thing on the read side over here in the tweet viewer. It gets invoked whenever there's a new entry in the Redis cache, and the developer doesn't have to learn how to go and be notified how to pull the Redis cache. They don't have to learn how to even read from Redis cache. They simply read the Dapper state store API. And that does a few things. One is they don't have to learn all these SDKs or incorporate them into their code. That also gives them incredible flexibility and portability, because they could replace Redis with Cosmos DB or some other, or Cassandra. And that is almost basically effectively, from a developer's perspective, a transparent replacement. So this makes this code extremely portable. It can go to the edge with Redis cache. It can go up into Azure with Cosmos DB. It could go to AWS with DynamoDB, with very little change or no change from a developer's perspective.
So a couple of questions. Let's keep this up because I'm looking at this. So this is one instance of a Dapper sidecar, or is it 3 for every? Is it 1 for each of the processors / code that's been written?
It would be 1 for each. And if you take a look at what I'm going to be doing is running it on a Kubernetes cluster. So there's going to be different pods here, one with its own sidecar. And these sidecars either can come as a sidecar container or as a library that is just loaded in there and exposing a listener on a local HTTP port. So Dapper is really something that you can consume. You can leverage whatever capabilities you want from it. If you want to use state store, you can. If you want to use service invocation, you can. If you want to use just its metrics capabilities to log interactions between different components, It really is a kind of pay for play. You take advantage of what you want, which makes it incrementally adoptable. You can take existing code and then say, I'm going to Dapperize just this one part. And I can do that whether I'm running an ASP.NET front end web server, or I'm sitting in a microservice-based containerized Kubernetes application. It really can go anywhere.
Which is really cool, because as I was looking at this, because you mentioned it could be an SDK or a container, you might have stuff that's just already running. Just put a Dapper sidecar container and it can now talk to it, and then it's now involved in the whole ecosystem of Dapper calls that you can make to it. Did I get it right?
That's exactly right. And I think that's what makes this so powerful, is that you can incrementally adopt it, and it just takes care of all the grunge work of doing throttling, queuing, message lookups, integration with these other services. All of that is just handled for you. So it really makes it. And let me show you the code behind this thing, and we'll actually run it to give you an idea. So here's the Twitter binding. So this binding concept we got from Azure Functions, which is incredibly powerful. It's just like I said, the developer doesn't need to write any Twitter code. They simply do this declarative specification for how they integrate, how they register with Twitter API. We're actually going to look for tweets that reference Dapper right now. So if anybody's out there and wants to tweet something, hopefully something safe for family viewing, feel free to do so, and the app should pick it up. Here, I mentioned that the code that reads the tweets through Dapper, you can see it's referencing a Dapper endpoints here, and one of them is the tweet store to save tweets, that state endpoint, the pub sub endpoint to write the published tweets over to the viewer, and then the service endpoint here you can see is the sentiment analysis service that Dapper is going to invoke. So it doesn't need to know where that sentiment analysis service is. It just invokes it using this local URL, and Dapper knows where it is. So it will route the call over to it. Now, if we look at the tweets handler, this is what the Twitter binding is going to invoke here. Just write a simple web server, get invoked at tweets, which is what we specified in that binding. And then what this is going to do is go over and call the sentiment API here, and then save the content to the Redis cache, and then also write it to the Redis cache in the pub sub to the viewer. If we take a look at the sentiment scoring piece of code, which is also going to be, let's see if I can click here. I don't know why click is not working on that.
That's okay, but I'm getting a sense for it's basically you declare stuff to point to the right place in Dapper, and then Dapper takes care of the rest. Am I getting this about right? That's cool.
That's about right. And I'm showing you the full code for this whole app. This is it. This is the sentiment scorer, which calls the cognitive API. So that's the cognitive API endpoint here that is going to call, get the score back, and then return as a result. Here you can see it returning the result, the sentiment score, back to that front end that was listening to tweets. Which is then going to save the tweet plus the score, also write it to this Redis cache endpoint, which then the final piece here is this Go front end, which is going to be reading from the Redis cache and then viewing them in a front end. And here's its binding to say, hey, when something shows up in this Redis cache, invoke me, and then I'll display it. And now let me just launch these three. That's the tweet reader. There's the sentiment score, and then finally the viewer.
I mean, as it's going, I mean, this is actually really cool, because you can take away from having to think about how to send messages all over the place and get services to talk to each other. Instead, you can focus on the actual part of the application, which is reading tweets and doing sentiment, right?
Yep, that's right. And let's see if we've got any tweets coming in here. So this is where I've got it listening.
Again, send your tweets to Dapper.
And then we'll Mark write more fiction. Not really a Dapper tweet, but I appreciate the support for my writing. Dapper's amazing. So you can see these are coming in live. And what you saw was all of the code from that app. There was no Twitter code. There was no Redis code. And like I said, you could plug in other pieces of code. And that app now is resilient and scalable and portable. And really, the developer just focused on what they wanted to do here, which is get tweet sentiments and then display them in this UX.
Well, Mark, we have only about 30 seconds, so if we could go back to your face, and if you could tell us a little bit more about where people can go to learn more about this, that would be awesome.
So actually, Dapper.io is the place to go for learning more about Dapper. Also, Mark Fussell, who's the program manager for Dapper and the incubations team, is going to be giving a Dapper talks. I think one today, two tomorrow, I think is what his schedule is. But just check the build agenda.
Well, I'm excited to see what else your incubation team comes out with. Truly, there's a lot of cool stuff. Mark, truly a pleasure having you with us. We appreciate your time. Well, as we say goodbye to Mark, we say hello once again to my co-host, Donna. Take it away.